Good afternoon, dear colleagues. My name is Elvira Jumala, and I am pleased to present our research entitled The Concept of Developing a Digital Twin based on the FIWARE framework for effective air quality monitoring in urban areas, conducted by our team at Lviv Polytechnic National University. The paper focuses on improving environmental safety in cities through innovative digital technologies. With rapid urbanization, air pollution has become a critical issue impacting health, ecosystems, and quality of life. Traditional monitoring systems often lack responsiveness. That's why we explore the use of digital twin technology, real-time virtual representations of urban environments, for more effective air quality control. The aim of the paper is to explore the use of FIWARE-based digital twin technology to create an urban air quality monitoring system. This study uses the FIWARE platform, which supports open standards and real-time data processing to create a prototype digital twin capable of monitoring pollutants concentrations, predicting their spread, and providing recommendations for reducing environmental risks. The methodology covers several sequential stages: defining the goal and object, collection and structuring data, creating a virtual model, data integration and visualization, developing application scenarios, and training and calibration the system. Each stage is described in detail in our paper with a focus on data sources, technical aspects, and their role in the implementation of the system. We choose FIWARE platform because of its open architecture, modular design, and support for NGCI LD standards. It enables integration of heterogeneous data sources, sensors, weather APIs, industrial systems into a single decision support system. Also, FIWARE platform was chosen as the basis for data integration due to its modularity, support for open standards, and ability to scale for urban ecosystems. Collection data from the physical environment is a key step that provides the basic for the digital twin to function. A network of IoT sensors deployed in the urban environment, including gas analyzers, for measuring PM 2.5, PM10, NO2, CO2, and O3. Temperature sensors, humidity meters, and atmospheric pressure sensors is used to monitor air quality. These sensors, for example, AeroTrack or Purple Air models, are placed in 20 key points of a simulated city: residential areas, industrial zones, transport hubs, and provide time-stamped data every 10 minutes. Air quality data is partly obtained through cooperation with local environmental services and open platforms, such as the Air Quality Open Data Platform, which contains historical pollution datasets for the region. Meteorological data, including through the Open Weather Map API, as well as regional stations that meet World Meteorological Organization standards. Additionally, information systems of industrial facilities obtained through the API of local enterprises provided data on SO2 and CO emissions, which are correlated with meteorological conditions to assess their impact. All data is structured in accordance with the OGC Sensor Syncs API standard, which ensures compatibility and processing in an integrated system. The creation of a virtual model is the core of the digital twin, providing a comprehensive display of the ecological environment. The architecture includes sensors that measure PM 2.5, NO2, CO2, and weather data. This feed into the IoT agent and Arion context broker. Quantum Leap stores time series data, while Grafana and Wirecode while cloud visualizes it. Key-ROC ensures access control. Data integration could cover physical sensors, open data platforms, and meteorological sources. Also, Sentinel-5 PM, satellite data, and drone measurements for spatial coverage and validation in hard-to-reach zones. Forecasting is done using recurrent neural networks trained on historical pollution and weather data. We also apply physical models like Gaussian plume to simulate dispersion. In testing, our system achieves 88% accuracy with a 25-second response time. In addition to recurrent neural networks models, we used Gaussian plume models to simulate pollutants dispersion based on wind and topography. This hybrid approach improves forecast accuracy. For example, during high traffic hours or industrial activities, the system can predict critical zones and suggest preventive actions. Visualization is a key to usability. The system displays live air quality data via dashboards, heat maps, and the mobile apps. Users get alerts when the pollutants levels exceed safety thresholds, enabling timely action. Dashboards not only present data but also allow environmental services to filter by zone, time, or pollutant. The system sends alerts via mobile app and bot, which is especially useful for vulnerable population like children or elderly residents. We tested the prototype in a simulated urban area with industrial activity. With 20 sensors and open datasets, we achieved 88% forecast accuracy and 95% success rate in real-time alerts. We conducted a detailed simulation in an industrial urban zone, and the alerts triggered during peak NO2 levels were validated against real meteorological conditions. Moreover, the system helped identify 3 optimal new sensor locations to improve coverage. The study confirms the effectiveness of digital twins based on the FIWARE platform for monitoring air quality in urban areas. The development prototype integrates data from IoT sensors, weather stations, and open source, providing tracking of pollutants, PM2.5, NO2, CO2, and forecasting their spread. Testing has shown 88% forecast accuracy and a response time of 25 seconds, and automatic alerts have reached 95% success rate. The use of open NGSILD standards and FIWARE's modularity makes the system adaptable to different cities. The practical value of the prototype lies in the operational management of environmental risk and raising public awareness. However, high infrastructure costs, the need for sensor calibration, and cybersecurity remain challenges. Further research could focus on integration with platforms such as home assistant, modeling transportation impact scenarios, and collaboration with global environmental initiatives, which would strengthen the role of digital twin in ensuring sustainable development. Thank you for your attention. I'll be happy to answer any questions via email.